Hey, good afternoon, everybody. Thanks for joining us. I'm Bob Lucero, Executive Director here at the Northern Virginia Regional Commission, and I'm glad that you could join us for this interesting webinar about district energy, fueled in part by heat export from a data center. Northern Virginia has the highest density of data centers in the world, and we're not talking about things that are happening across the Atlantic. We're talking about things that are happening right here in the continental U.S. With that, I would like to turn it over to my colleague Dale Medeiros, who's been a leading proponent of district energy systems here at NVRC for the last 20 years since we've been working on energy-related issues. So with that, Dale, I'm going to turn it over to you.
Great. Thanks, Bob. Thanks also, Tom, for joining us and John and everybody that's taking part in this webinar. I'm Dale Medeiros. I have the privilege of working with Bob here at the NVRC, coordinating a lot of the energy and sustainability portfolios. And we're a regional council of governments representing the 13 counties, cities, and towns of the region. And as Bob said, we have approximately 250 data centers with more in the way. We have the highest concentration of data centers in the world, and they play a very pivotal role in our economic health and the environmental fabric of the region. And as our local governments look to preserve this balance of economic benefits and environmental performance through data centers, especially in light of the anticipated demands for energy over the next 10 years, they're looking across the country and also the globe for ideas. And so one of the most practical examples of where residual heat's been conveyed is in Seattle, the Denny Hill project. And they've experimented successfully with district energy. It's emerged as a viable means to promote sustainable energy management in Washington, and we see it fitting comfortably under the Commonwealth of Virginia's all-the-above approach to energy policy. And so here today we have Tom Marseille, professional engineer and managing principal of the Sasan Group. Tom's going to share his involvement with the design, planning, and construction of the Seattle Denny Hill neighborhood and give us some insights into the project's financing and operations. A little bit about Tom. He's an award-winning mechanical engineer and recognized as a pioneer in the design of ultra-low and zero net energy and carbon-neutral projects. Tom's an expert in leveraging performance analytics and life cycle asset optimization to inform design decisions. Tom fosters an integrative and collaborative approach that consistently leads to actionable plans for clients and outcomes that are robust, resilient, resource-responsible, practical, and maintainable. Tom has also led feasibility studies and designs and served as owner and technical advisor for modernizations and new innovative low-carbon district and campus central heating and cooling systems for public institutions, private companies, and district energy utilities. We're also here to have a very authoritative voice on local governmental energy management from Fairfax County, my friend John Morrill. John has a long-term history with holistic energy management, going way back to the days in which we worked together in Arlington County. John?
Well, thank you very much, Dale. Very much looking forward to this webinar. We looked at district energy possibilities in Arlington over a decade ago and found central cooling and central heating systems linking multiple properties was a sound idea, but still challenging due to private property issues and getting mutual interests aligned. But it remains a compelling idea for maximizing the efficiency of thermal energy. Managing thermal energy, or heat, is often at the heart of good energy management. Most of us know this is the case when we want to keep hot stuff hot and keep cold stuff cold. Insulation is critical for those situations, whether you're speaking of your home where you want to be comfortable, or an insulated container for a cold beverage on a hot day. On the other hand, there are cases where something gets hot and it needs to be cooled off for best performance. For example, your car has a radiator to cool a gasoline engine and a cooling system for the battery if it's electric. So that is the case with data centers. The computer servers in data centers get hot, and they need to get rid of that heat to work efficiently. Air conditioning a data center loaded with computer servers gets expensive and uses a lot of electric power. So data centers would love to get rid of that unwanted heat easily. And that's where this webinar comes in, describing an approach that can serve mutual interests. Back to you, Dale.
Thank you so much. So the program is pretty straightforward. Tom is going to share with us through a series of slides in his PowerPoint, his work in Seattle. And then we'd like to hear from you and engage in a question and answer session. So please put any questions you have into the question and answer box, and we'll answer them chronologically as best as we can. And we look to wrap things up by 1 o'clock. Tom, the floor is yours.
All right. Well, thanks, Dale and John. I appreciate the introduction, Dale. It's always funny hearing someone read your bio and things like that. So anyway, I'm glad to be here. I'm glad to be virtually here with you guys today. And we'll be talking about this really fun project. Probably parts of it, I would say, was the pinnacle in terms of interest for me in terms of projects in my career, actually, when you talk about the entire Amazon corporate headquarters, which we're not going to be talking as much about as we are the Eco District. And how we're heating the Amazon headquarters through this concept. So let me just get this rolling here. I think I got it going. There we go. So the agenda, well, you've got the introduction, so we're going to go quickly through that. And then I'm going to restate a little bit what this thing is. What is it we're doing, and how, and then why does it matter? At least from the perspective of the two parties involved in the city of Seattle. How does it work? Just kind of a fast fact on how this thing actually functions the way it does. A little bit more on benefits and impacts. And then we're going to spend a fair amount of time talking about bringing the deal together, because end of the day, yeah, there's technical aspects to this that need to be overcome. And good engineering can get you there for this kind of a concept, because conceptually, it's not that difficult a concept for most people to understand. You may already understand it from the introduction we've had. But really understanding what it takes to get a deal between two private parties within a downtown core of a city is really kind of the interesting part of this, I think, or a lot of the interesting part of it. We'll sort of summarize with some lessons learned, and then we're going to kick into the Q&A, which I'm sure there'll be some good questions, and I'll be looking forward to some moderated questions from John as well. So you had the introduction on me. So I don't have to talk about that too much, other than to kind of give the very specifically what my role was. So I was hired essentially by the architect who was designing the Amazon corporate campus. So really hired by Amazon. And I ended up being, I was the principal in charge. I was leading the mechanical engineering design, and I'll call the building performance analytics, so to speak, as we were trying to look at this deal, but just really understand how the buildings were going to perform. And I was doing that for the Amazon campus, including the spheres. If anyone's ever seen that or visited that, it's kind of the jewel of the campus, if you will. And again, one of the most favorite projects I ever worked on. So I was on that side, if you will, on this whole project, on the Amazon side as the engineer for that system. So the Eco District, as it was coined, this is just, the sort of the definition is an innovative heating network that thermally connects Amazon's downtown headquarters campus, which is over 3 million square feet of workplace assembly spaces, with the neighboring Weston Data Exchange. And so the data exchange is essentially a major telecom carrier hotel, as they call it. And so within that building, there's many small data centers that are all connected within the sort of the same mechanical system that's, as John mentioned, has got to get rid of that heat that's generated by all that data being processed. And so, really conceptually, the Eco District was how to bring these two people together for this sort of district energy application between that Weston Data Exchange and then this downtown headquarters campus, which is actually, as it sits right now, it's closer to 4 million square feet, 4 high-rise towers, and then assembly spaces and different buildings in the spheres. So how does it work? If you look at the photo, sort of center left, a high-rise building there is the Western Data Centers, or the Western Data Exchange. And so that operates as data centers do, excuse me just a second, 24/7, 365 days a year, 11 megawatts hours of power daily. So if you're an engineer and you're designing systems, and let's say you're putting a boiler in a building, and it's got to be, that boiler's got to be there to heat the people and make them comfortable, there's a certain reliability you can expect with that, and you can expect failures and things like that. One of the things that was really interesting about this is I don't think I could come up with much more highly reliable source of low-grade waste heat than coming out of a data center, which because of what its function is, inherently is highly reliable. It's got backup power, backup systems everywhere. That having that data center down for any amount of time is money. And that's what really, that's what's driving, that's the big thing in the data center, keep everything working. And so for me, that means I've got a highly reliable source of waste heat that's just going to be there. And so, you guys were talking about all the data centers in your area, in your region. I mean, that's a tremendous resource. And it's a resource that, literally, if it's designed as a data center is typically designed, is never going to, you're never going to turn off the tap on that. So it's really reliable. Anyway, so there's that heat source, which are these data centers. And then there's the thermal exchange. And so this waste heat, if you will, is I'm going to call it low-grade heat, which is still useful for us. It's going to be water, basically. And so you're basically taking water from that building that's sort of center left and going across the street to that building, which is to the right, which is the Doppler building, which is the first of the Amazon buildings that was built. And that's 6th Avenue. And this is actually a view from my office. So I'm looking, I just took this literally last week and said, oh, I'll just take a shot. You can see off in the distance there, the Seattle, the Space Needle, so you know it's in Seattle. But basically that was the thing, is we got to connect this building to that building and basically pipe across the street and connect to the central plant in Doppler, which is also a cooling plant as well. So that's low-grade waste heat, which is what you can typically capture easily. And that waste heat can be used a lot of different ways. We sometimes call it an ambient loop in the district energy world, but essentially, or a condensing water loop. But they're using it to cool. That water is cooling the data center. Typically, be going up to cooling towers on the roof. In this case, it doesn't have to. It's coming across the street to Amazon. But what has to happen when you get to Amazon to make it useful heat is you need what's called heat recovery chillers, and you can sort of see those here in this photo. And they basically working through a vapor compression refrigeration process, if you will. I'm not going to get into the details of that. They're going to extract heat from that low-grade loop and put it into the heating water loop of the building, which is at 130 degrees, which is what you need to heat the campus. So when we designed the campus, we designed it for 130-degree heating water. And so that differential between the 65-degree waste heat and that 130 is very achievable in terms of using a sort of a conventional product on the market at the time. They've got more products on the market now because we're really moving more in the direction of heat pumps. But this was a very off-the-shelf type of a chilling product. So it was, very, very reliable, very understood as something that would work for this application. So you've extracted the heat from that loop of water, or the water that goes across the street to the Amazon building. You've cooled it by extracting heat from it. So you send that cooled water back through the eco-district system to the Weston, where it can be used to cool the data center servers again, that then reject heat back to that loop, which then goes back to Amazon. So you basically have a continuous, highly effective or highly efficient thermal circuit that goes between the two buildings. So, there's lots of reasons why this matters. I'm going to talk about impacts and things like that, but, this really is what's unique about this, as to my understanding at least, was that it was a cross owner. It wasn't a district energy plant like you see in the bottom center there. It was this data center, which you see on the bottom left, which was owned by one entity, Kleist Property, and then ported over to Amazon. And so you needed to have this cross owner arrangement on an urban scale, and a fairly large one at that, for waste heat recovery. And so it basically turns this data center neighbor, into a mutually beneficial energy source that could be used by other buildings. And we'll talk about how that's arranged within the context of the deal that was established. But it's, it can be a replicable model as long as you've got a source of heat. If it's a data center, I mean, there's other sources of heat in an urban context. We're talking data centers today, but I mean, we've also had projects in Seattle which have looked at, the large sanitary waste lines that are basically going through the city from King County. Those big waste lines, that's also a reliable source of heat to recover from. And so people are looking at sort of waste heat recovery from sewer lines is another thing. But anywhere you've got, a reliable source of heat, in this case with, two different private owners, you have an opportunity to do that. So we think it's an important one, and I'm really happy you guys are sort of picked up on that as well. So benefits and impacts for Amazon. I'll start with this one. Carbon reduction. Energy saved equates to avoiding a lot of CO2 emissions. around 65 million pounds of coal, which is, again, you have to figure out what lifetime you're talking about, but that looked like a lot, and that is a lot. Over 4 million kilowatt hours of annual energy saved, about 80 million kilowatt hours over 25 years. This third one is a big one, though. I want to sort of dwell on this. The campus isn't being built out in one, you can't build out an entire campus, all the buildings at the same time. They were coming over time. And it was, as we started this project in 2012, I believe, is when we started master planning the campus, maybe a little bit earlier than that. But there's all these millions of square foot of buildings didn't happen, in 2013 or 2014 when this deal was being arranged. It was going over time. And Seattle has a very stringent energy code that's been sort of getting more stringent with each code cycle. We're probably one of the most stringent, if not the most stringent in the country. And so Amazon was looking at this and saying, what can we do? How can we set ourselves up for compliance with this energy code? And they also were like, we don't want to end up having to have apples in one building in terms of the system, but then we have to put oranges in the other building because we need a different system that's going to meet the current energy code that's then going to be available at the time or going to be required at the time. So we basically said, look, and we did this analysis, this performance analysis, said, look, we can standardize your HVAC systems across multiple code cycles as the campus is built out, because we're getting such a high efficiency source of essentially free in terms of waste heat that's available to them. And so for them, that was very attractive. It meant they could sort of standardize on the systems they're putting into the buildings. They also, the idea of it, and by adopting this concept of a district, they could sort of help reduce the amount of total equipment they had to install in all their buildings as well by interconnecting them through capturing waste heat from the eco district. So that became a compelling thing for them, as these multiple code cycles. They could sort of set themselves up for compliance that way as they built out their campus. And then finally, there was a lot of alignment with the city in terms of aspirations. And this, as we're going to talk a little further, really helped enable the permitting and review process and really buy-in from the larger community, because Amazon's a huge employer in our area, even with Virginia now making some inroads. And there were some people that were like, well, what are they doing for the community? And well, they were doing something. They were a really good story here to say what was going to happen and how they were being responsible for what they were, how they were coming into the community and how they were going to approach projects like, for instance, spheres, and make it energy efficient. For Kleist Properties, that was the owner of the data center, Kleist Properties. They got energy and water savings. And so for them, they had rooftop cooling towers, which are used, well, they use them year round, but during the heating season, they use to reject heat from these data centers that are continually producing heat. So they can reduce the operation of those cooling towers. I don't know if this turned out to be the case, but they were looking at a way to expand their systems within the building, or to add more cooling or more servers in the building. And they thought maybe there'd be an opportunity to expand that without having to add more cooling towers, because they were giving away some of that heat. Extending equipment service life, you've got less runtime on the equipment. It simplifies the maintenance. Again, this is a 24-hour facility. And so if you don't need to be using those cooling towers all the time in the winter, you have an opportunity to actually maintain them. So the other benefit is they got into this eco-district agreement that they will talk about. They're one of the parties to that agreement, or one of the entities under the eco-district, that allows them to basically, if there's future growth with other potential customers, they can do it. There's obviously some safeguards in there for Amazon, which we'll talk about. And then basically, they held the equipment risk, but they landed this recurring revenue stream, which, really was very attractive because it wasn't that expensive for Amazon to buy this waste heat. And they also had full asset ownership, which gave them whatever value they could get out of the eco district with Amazon and other parties going forward. So bringing the deal together, it really started first with understanding, what do you need and what do you have? And for what do you need, this is, what is Amazon heating demand requirements? And so, energy models, some of you know that terminology, but basically you create a model for the buildings that are going to be built, and you're trying to predict what those loads are going to look like. Not only the peak load, so you know how to size a system, but also what's it going to look like over the course of the year? How often do you need heat? In Seattle, we have a very mild climate. We do get some cold winter days, but there's lots of time during the year where you may need a little heat in the morning, but then you don't need heat in the afternoon, say. And so understanding, what is that amount of heat you would actually need to have, that you could then understand in context of a deal like this, what you're going to want to buy or potentially buy. On the Weston side, the Weston Data Exchange side, they needed to understand what their resource was. And so, I mean, it's a fairly simple calculation in some ways if you know how much equipment you have installed to know how much heat's going to be generated from a data center. But they also were able to measure that because they had years of operation at that point. So they had an idea what they had available to them. And so again, there's kind of a balancing act in the deal from a thermal standpoint. And for Amazon's purposes, they had to figure out how much energy are we going to need, or how much thermal energy do we have as demand initially when they build the first tower, and how much are we going to have when we add the next tower and the next tower and the next tower. So it was kind of an interesting modeling exercise, and we had to figure out how to best use that resource spread across all these data, or excuse me, across all these high-rise buildings and meeting buildings such as the spheres. So then there was economic feasibility modeling. And so this was the financial modeling that had to go into it as well. And so both sides were doing this. I was on the Amazon side and helping to do some of the calculations for that and come up with some of the inputs to that model. And we were comparing it against standalone HVAC solutions, because Amazon is like every other building owner, is initially going to be a little risk averse to trying something that's this unique and this different. And so whatever process or whatever roadblocks you guys might be coming up against over there from a owner reluctance side related to risk for themselves, Amazon is probably a good model, because a lot of the things they had to go through and think through are probably going to be analogous to some of the things you guys would be thinking through. So from that standpoint, they still wanted it to make economic sense. They were not looking for it to be cheaper day one, and it wasn't. There at the time of when we were looking at this first building, there would have been a cheaper HVAC system they could have put in. It's not one they wanted to put in, but they could have put a cheaper one in than they did put in. And then there could have been, and then even the one that they could have put in that was standalone was probably less expensive than what they did to connect to the eco district as a first cost standpoint. So it needed to have a payback. And so that's what a life cycle cost analysis will give you. And so they were doing that for lots of different scenarios. I think we had at one time, I'm going to say we might have had 10 or 12 different options going at the same time. We were looking at various permutations of connecting to the eco district and various permutations of standalone as we were trying to figure out the best way to move forward. And so there was a lot of calculations going on early in this thing. So that's the sort of my side of the world. Probably should have started with this actually on the very first slide. I said very early on in this thing, when the deal first looked like it was going to happen, but even before the deal happened, I was noticing there was one individual. I mean, we all were sort of interested in this, but we're all, if you're talking about a project team, managing our risks, so to speak. There was a contractor, a general contractor on board. They need to manage their risk around cost. Amazon wants to, manage its risk around cost and future operational risks. Everybody's kind of got that going on. And what that tends to do in a building market is and I think it's traditional for the construction industry, is we all gravitate towards business as usual. If you go towards business as usual, you're mitigating your risk. And so if you're an engineer, in my case, if you're designing the same system you do every single time, you're mitigating that risk. So we all saw this as a good idea. There was a momentum or inertia, I guess you'd call it inertia, though. There's inertia to not going in this direction that wants to pull you back towards business as usual. But in this case, we had an advocate. We had an owner rep who's now retired, a great guy who really grabbed a hold of this thing. And at every single meeting, there was lots of things to talk about besides just the eco district and whether we're going to make this happen. He would bring it up. He would not let it go. And so having that person there who's, talking to people, all the different kind of stakeholders, finding out what's holding things up, you need that champion. And that I can't overstate that. I think you really need that champion. Somebody who's just a bulldog for this concept on that team, who has the ear of the owner or the owners in this case. Real quickly, you need to have good engineering on both sides of the transaction. I won't try to explain the diagram there, but that's our central plant for the Doppler building for Amazon. You got to understand what all that means and how to pull it all together. So all other things are required to bring the deal together is you need you couldn't just have Kleist properties with the Weston Data Exchange and Amazon, and then sort of what happens in between. you needed a legal entity. And so a new legal entity, this Eco District LLC, was created. And their job was basically to own and operate the waste heat infrastructure, of which maybe you're figuring out a lot. There's not a lot to that. It's really just that those pipes across the street, some heat exchangers, some pumps. It's not a lot because there's the systems in the data center that have to operate to maintain the data center cooling. And then there's the systems in Amazon, which was really on the other side of the transaction, which we designed. But there needed to be this legal entity. There needed to be this clarity of infrastructure separation in terms of ownership and liability, and how it's separated from the Amazon system, and how does it give sort of risk protection for both sides. And then really, this was another thing that we spent a lot of time on thinking about, both from sort of a technical design aspect and a legal aspect, is severability. So, you're going to get, and this is a deal, this is a question you get into when you get into any city district energy system. We have city steam in the city of Seattle, and that's how a lot of the buildings in downtown Seattle are heated. I don't know if any of you have district energy systems that are sort of legacy. You've got those things in there, and it's really hard to figure out how do you move from that to something else, because right now we're looking at how do we move from using central steam to electrification and decarbonization of individual buildings. And you start to run into some technical hurdles there really quickly in that, and that's a whole nother topic than today. So we were trying to think from a technical design approach, how could these buildings be severable? And then to throw one other little wrinkle in it for us, Amazon's like, okay, we want to understand how we could operate on our own if this deal ever happened or ever ended, or for instance, the data exchange shut down or something like that, how are we going to operate? And so they needed to figure out what that technical solution would look like. They needed to know, the city needed to understand that that was going to be something they were going to need to be able to do potentially in the future, and understand it. And so there had to be sort of an approach that was sort of nodded by the cities. Yeah, that would work for us too. And then the other little wrinkle was Amazon said, in the future, we could always sell our buildings off. And if we sold our buildings off to somebody else and they didn't want to be part of our little central utility system that connects all the buildings, how could each of the individual buildings operate on its own? So we had to think through, from a design standpoint, all those different sort of technical approaches to severability, while there also had to be considerations for the legal severability. So that had to be baked into the deal. So bottom line was, and this is actually, it was operationally a good thing to do, which we can talk a little more about, is Amazon actually has some boilers in their building, and they're not buying all their heat from the data centers. There's actually a limit to what they can provide and these kinds of things. So there were some technical aspects to that, but they have boilers. They have the ability to still operate on their own if they needed to for whatever reason. That was part of the design. So then I talked a little bit about permitting. I mean, this is, even though it didn't look like a lot of piping, we're getting from one side of the street to the other, you're interfering with a lot of stuff that's in the street already. It's always the problem when you're in existing city streets with the infrastructure that's already going to be down there. You have to figure out how to get things across and get things around. And so district energy providers know a lot about that. And we basically had to go through the same thing because the Eco District essentially became a district energy provider in terms of this transaction. But as I said, there was some good momentum behind it because the city was interested in the deal, but there still was a lot of regulatory approvals. And they took, 9 months by the time you got done with talking to the Department of Transportation, the City Council, and other various departments. That took a long time. And so really, in understanding and bringing the deal together, you had to understand who you needed to work with and really what was in the ground and figure out how to do that. And then finally, one other reason for why the Eco District was important is the delineation of responsibility. There had to be an agreement that clearly delineated responsibility for maintenance, street access, some of the disruptions that would have to happen when you were installing it due to the infrastructure under public rights of way. Again, that's not unique to this. That's typical for district energy systems. They have to think of all those kinds of things. But for us, we had to sort of do it as a one-off for this application, which hopefully then is extendable for others in the future. I'm not going to talk a lot about the data in terms of how it operated, because a lot of that data is sort of proprietary to Amazon, but we were keeping data and track of data at the beginning, and we were tracking the usage relative to our model, relative to the contractual obligation, which is that green band across the top in terms of what sort of is the expected amount that would be purchased within the contract. And so, and this is over the course of a year, showing a full year and then the next year after that. And you can see when the first year was 2017, and then in the 2018, you can see part of that. But they've been doing it ever since. I had lunch, when was it, last week? Week before last, I guess, with the sustainability lead mechanical engineer, if you will, for Amazon, and this thing's chugging along. And so they're happy on their side, and I think Kleist is happy as well. So how am I doing on time? I'm doing very good on time. I'm going to go now to my lessons learned, and then we actually have time for lots of questions. So when I talk about, available waste heat sources, the data center is a great one in this case. It was proximate, which is sort of number 3, which helped simplify things and lower cost. But it's identifying those opportunities. It's, when you look at a new project or you look at an existing building that may be trying to do something, it's like, what's going on in that building that could make it more efficient? Are there available waste heat resources around that building? What can you harvest and capture? And so understanding the opportunity, which, again, we actually, in this particular case, my company at the time, WSP, was looking at various opportunities like this, again, sewer heat recovery, data centers within buildings. And once we heard about the data exchange across the street, we're like, oh, there's the opportunity. Meanwhile, on the Kleist side, they were looking at Amazon, and their mechanical engineers, McKinstry, was also saying the same thing. Hey, look, there's the opportunity. So understanding the opportunity, and then, as I said before, talked about, you really need to understand the loads and what those loads are going to be and when they're going to be over the course of a year, so you know what your demand is and you know what the availability of supply is, and kind of getting those two and bringing them together. The challenge that you may get into when you start talking about, actually making this happen in Fairfax County, is, how proximate are those heat sources to the demand? And, the more spread out things are, or the more the load, or I'll say the demand may grow over time, because if you're building out a campus or something like that, you may have a sunk cost initially to get that connection going, like Amazon had to do the sunk cost and bringing the eco district connection over to the Doppler building. And then but they were able to build things out over time. And so it's a question of how, can you afford to do that sunk cost early on? And it gets easier the more proximate things are to each other. You got to have those champions. Deals for really good ideas fail often because they say they're just too hard. And they're too hard, again, because people are trying to minimize their risks. Business as usual is a default mode for a lot of people. You've got to be willing to, take some chances. We took, for this one, we did not feel there was a technical risk, but it wasn't being done, right? And so people don't, when they say here it hasn't been done before, that triggers alarm bells for people. And so you kind of have to, you fall into the, gee, we can do what we've always done. We know what the costs are going to be. We know exactly this is how it's going to go. And so, so trying to avoid that, it's too hard, and you need the advocacy to do that. You have to do the economics. You got to do them thoroughly. You've got to, both parties need to use them in the decision process, I believe. And then the engaging early. I think this was the other one, is it's a long project we had, but you need to talk to those authorities, the regulatory agencies, the utilities. This particular deal, I'm trying to think, I don't think we needed to have as much interaction with our local utilities as we normally would, other than as we needed to coordinate for bringing pipes across the street. It did require a separate district energy vehicle, in this case, the eco district, to clearly help separate the risk and understand governance. And then you need an energy performance agreement. And so you needed a fairly long, flexible energy performance agreement that addresses performance guarantees, escalation, continuity of service. It's essentially what you would have for a district energy system. It's just, again, the uniqueness to this one is having not a district energy provider on one side and Amazon on the other, or a consumer on the other, but private party on one side, district energy in the middle, and then another private party, so being the unique thing. And then you really need to understand the timelines. I think that's going to be a key thing as well, because they can stretch on for many months. And again, the time factor is a money factor. Time factor can be a reason that people say it's too hard. Anyway, not to sugarcoat it, but that's going to be really important. All right. I have got through my deck. I can go to Q&A now.
That's great. I'll let John orchestrate the Q&A. Take away, John.
Thanks, Dale and Tom. There are 13 questions here, and I think a number of them initially are kind of in the weeds of the design of the system, which you've I think answered a number of these, but just to quickly go through,
Sure.
did the data center still install cooling towers in case the heat recovery system went down? And I
Yeah,
believe you mentioned they
they
did.
had the cooling towers already. This was just an opportunity for them to save energy, water, and potentially be able to extend their overall capacity of the data centers by having, basically another way to reject heat.
Okay, thanks. And then what's the delta T on the condenser water? So it goes from 65 degrees over to
Eight to 10 degrees.
oh,
It was
it's
8 to 10
okay.
degree delta T. Yeah.
Okay. I'm not sure I understand, could the temperature of the data center be increased by modifying the data center cooling system? Because I don't think we want the data center temperature to be increased.
Well, you could. I mean, that would get kind of into the side of the equation I wasn't in. But I mean, data centers now, a lot of them are operated at higher temperatures than they used to in the past. So, you theoretically could have higher temperature water coming out than you would have than when they designed this one. So yeah, you definitely could have. You just kind of have to understand what the limits are and how the design is set up. But I mean, some data centers are now operating, at 90 degrees and things like that, and you could end up with warmer waters. That would make things more efficient, but that's not how it was designed in this case.
Okay. And then how is the Amazon campus cooled?
So there's heat recovery chillers, which are taking this waste heat source and boosting it. And in a pinch, those heat recovery chillers could operate as water chillers. But there were also additional chillers in the building that were really sort of more efficient and designed specifically for summertime cooling. So they sort of had both two sources. They had just regular, but if you saw one sitting next to the other, they look identical. It's just one is size and the compressor's been sized for heat recovery, and the other is specifically for water chilling.
Okay. And I think related to the first couple, is there a backup or overflow system if the data centers need more cooling than the Amazon offices need heat? And if so, how's it provided? So I think you mentioned that the data centers do have cooling capacity.
Correct. The cooling towers are there. This was a functioning data center before Amazon came onto the picture. So yeah,
Good.
it was just an opportunity.
And so what's the thermal capacity of the system? You mentioned how important it was to calculate how big the flows are going back and forth. What is it? What is the capacity?
Let's see if I don't want to get this wrong, but I believe it's 5 megawatts thermal capacity is what the contract value was roughly.
Thanks. And so I think by your describing this as essentially as a retrofit of the
For the
existing
data center.
for the data center.
Yeah.
So next question is from one of our elected delegates to the General Assembly. He says, I'm working to have the Virginia legislature encourage or maybe require the use of waste heat from data centers. Can you talk a bit about the possibility and or challenges of retrofitting a system like this for an existing data center and any existing or future nearby development?
Yeah, it's really going to depend on the design of the data center, how easily it's going to be to recover that heat. If it's a fluid-based cooling system, then in theory you should be able to do it. And in this case, they actually had to make modifications in the data center because right now the cooling water was going up to the roof in the existing data center building. It's a high-rise building, but in this case they needed to bring it down to the basement where the interconnection was going to happen to go across the street. So there was definitely modifications, but as long as it's a fluid-based cooling system for the data centers, then it should be doable. I mean, there are some cases where they don't do that, but that would be the reason. That would be the reason.
Right.
It would be an easy question to answer, if you knew who, to talk to the people whose data center they had in terms of whether that would be a possibility or not.
Okay. And then related to that is what jurisdictions in the US or around the world, what are jurisdictions in the US or around the world doing to encourage the use of waste heat from data centers?
Well, that's probably a bigger question than mine. And, you know, John was just at the IDEA conference too. He may have some, or excuse me,
Dale.
might have something to add to that. But I will say that in Seattle in particular, and the state, I should say the state of Washington in particular, if I can digress for just a minute, we have in the state of Washington a regulation that's been in effect now for 3 or 4 years, and it's just starting to sort of bite people because there's a compliance period coming in. It's called the Clean Building Performance Standard in the state of Washington. And the Clean Building Performance Standard is mandating higher levels of energy efficiency in operation, so measured energy efficiency in buildings. And it's going to be requiring existing buildings of a certain size to demonstrate that energy efficiency over time. And then on a cycle basis, they're going to have to show at a particular point in time, which depending on the size of the building, they start to have to show compliance in 2026. They have to say, I hit a certain EUI, if that's a terminology, probably you guys know that one, but an energy efficiency for their buildings, and they have to demonstrate that. Over time, those buildings, you know, in the next 5 years, they'll have to show like more efficient and more efficient. And this is driving people in older buildings, especially on campuses, to say, how am I going to do this? I've got a central steam system on my campus or something like that. And so what the state has done is they provided some provisions through additional regulations for if you have a district energy system, provide an opportunity for a plan to make that transition. And so there's actually some things dialed into in the city, in the state, to allow people with data centers to create people with district energy systems existing to create plans for decarbonization of the portfolio of buildings over time. And so they're sort of giving them some incentives to do that versus having to follow the regulations as they're written in the Clean Building Performance Standard. That's a lot of words, but the answer is yes. They're recognizing the uniqueness of district energy, and they're providing pathways here in the state of Washington towards compliance with the Clean Building Performance Standard, recognizing the uniqueness of data centers and how you do that in here. So, but other parts of the country, I'm not going to be able to speak as readily to.
And I can send it to State Delegate Delegate Sullivan links to a really interesting initiative that one of our operators in Northern Virginia is undertaking, Equinix. They have the Global Heat Export Program, which is explicitly linked to share lessons and information about ways in which their operations in cities like Frankfurt or in Paris could inform equivalent types of programs, not just in Europe, but in the United States. I'd be happy to, after this webinar, send you a link to the program, because it's something we've engaged the firm with directly.
Thank you. And also, Tom, that a number of us are familiar with the building energy performance standards, and that's something that our neighbors in the District of Columbia and Maryland have the authority to put energy performance standards in place. We unfortunately don't yet have the local authority to have building energy performance standards, but that has been a pursuit for at times for a few years. Let's see, another question from a district energy expert, Peter Garforth, asks, and I think you addressed this, that there are parallels where large community district energy systems were developed near major factories, but then when they were closed, the community had to scramble to fill the gaps. And I think this is the
Severability.
Severability, thank you.
Yeah.
So he asks, what are the what-if conditions if the data center decides to shut down sometime in the future?
Yeah, and that's why I say we designed the Amazon system to be able to run standalone, and then also to be able to separate buildings if the Amazon campus ever severed from, you know, in terms of an ownership perspective, and them to run alone. So Amazon wanted us to think of that when we went into it. So there is the ability to heat those buildings without having to be connected to the data center. In fact, that's actually installed in place today if they needed to do it. Fortunately, they typically only use that for trim and for peaking conditions. They don't have to use it as their base load, because the data center is their base load. Or excuse me, the data center manages their base load and the heat we recover from the data center.
Right. Okay. Thanks. You mentioned the importance of setting up that Eco District LLC as an entity dedicated to this transaction. Who funded that to get it going, and how does it support itself? And I'm assuming that it's Amazon compensating for the heat they're getting?
Yes, they are compensating for the heat they're getting. And so there is an actual agreement in place for purchasing that heat. That is the primary funding mechanism.
And does the Eco District LLC have investors, or is it
Well, there's two entities that started the Eco District. That's McKinstry, which is a mechanical contracting firm. It's an engineering company as well, and Kleist Properties. So Kleist Properties actually has, sort of a legal separation from the data center group as one of the members of the Eco District as well. So they were the people that started it and founded the Eco District. So yeah.
right? Okay. Yeah. I think you might have mentioned this in one of the preliminary discussions we had, but what was the timeline from sort of ideation to construction to operations?
Yeah, so the 2013 project started in 2012 that I got my involvement. That's when we were sort of master planning and doing the early design for the Amazon campus. And I think it probably was late 2012, but really 2013, where I'd say the main design was going on. And that's when the deal was being discussed and various options were being considered, those kinds of things. And I would think the deal probably got struck late 2013. Then the first tower, the Doppler Tower, which is about 1 million square feet for the Amazon campus, was completed and commissioned and operable by 2016. And then 2017, when I showed that data, was the first year, like sort of first year of operation where we could really sort of see what was going on. So that was the completion of that building. Then the next building in the Amazon campus, first day, which was the second tower, that was completed. I want to say that was completed around 2018, which was also when the Amazon Spheres was completed because it was part of that building. I want to say that was around 2018, maybe late 2017 to 2018. So it came on shortly thereafter. And then the additional towers, I think the final one came online of the 4 main towers in the campus. And the campus, by the way, there's lots of buildings that are in this area that Amazon occupies, but these are the ones that Amazon owns. This is their actual headquarter campus that they own. And those got done, I would say the last one got done probably 2022, something like 2022. So you're talking probably almost a decade between ideas and the final building and the sort of campus build out.
Okay, thanks. Going back to, I guess, an engineering question, can you comment on heat demand? The questioner says, my understanding is that most commercial buildings have a lot more cooling load, even in winter, but less heating load. And that's certainly the case around here, where we have relatively mild winters and brutal summers.
Mm-hmm. Absolutely, you're right. And I'm not going to quantify it, but I'll speak about Seattle and I'll speak about the buildings. Yes, absolutely is the case. We have modest heating loads. We have some cold days where you definitely need heating. But a lot of the time, what happens in buildings and office buildings is there may be, like after the long weekend, there's sort of a morning warm up on the first day of the week to get things up to temperature. I see Dale smiling for some reason on that one. And then you could have, if you have cold weather, you have morning warm up as well. But in the middle of the day, what's happening, as the person who submitted the question rightly understands, you've got people, you've got lights, you've got equipment, you're generating heat within the building. And for the Amazon buildings, they're using, I don't know how people know these terminologies, they have a VAV system in there, which is able to employ free cooling using airside economizer. So there's cooling going on, even in the winter here. But that's, again, we have a mild winter, so we're not Minneapolis or anything like that. So it's correct. The heating is a lot less than cooling, but the cooling is free here. for the most part because the weather is mild for an office building.
Okay, thanks. Um, one of your slides outlined a number of the key things, but just to reiterate, what were some of the key tasks on the critical path? And did this overall take more time than the conventional HVAC approach?
Took a lot more time than a conventional HVAC approach. Conventional HVAC approach, we probably would have had, there were probably with a client like Amazon, who's very considerate about what they want to do, and will give it some thought. It's a bit longer process to come to a solution in terms of what design approach you're going to take. But we'd have just been modeling an individual building or buildings, and basically presenting different options for what approach you're going to use that are all standalone. And it would have probably been a process, and really the only person making the decision is them, right? There's not a third party. There's not an eco district. There's just no other parties involved other than them and whoever's reviewing their plan saying, yeah, it meets the permit. So it becomes a much more streamlined process. And they brought the contractor on board early so when we were evaluating different options for mechanical systems, the contractor could be there and saying, okay, this one's going to cost X, this one's going to cost Y. It was a self-contained system on the project team, if you will. There was no external stakeholders involved in this thing. So much faster. Would have been much faster.
Okay. And then I want to jump to, would it be helpful for localities to encourage district energy ready designs for new data center design and development? And if so, what does the concept of district energy ready entail?
So I'm going to interpret that to mean for the buildings that would be purchasing the energy? Is that what I think the question's asking?
Well, I think it's both sides. It's both, I think you mentioned that for data centers, if they had liquid cooling.
Hydronic-based system for cooling, yeah.
So the hydronic cooling on the data center side, but then accommodation for district energy ready on the customer side.
Yeah.
And if I could just add, my understanding too is, having been part of these conversations, is looking ahead to the future. If there, what can local planners and local authorities do in looking ahead, say 5 years, to cultivate potential demand or markets for district energy that would be linked presumably to data centers in the development of a plan or a set of designs that might not be built in 12 to 18 or 36 months, but 5, 6, 7 years ahead.
Okay, let's unpack the question a little bit. I'll start with, if you are a building owner and you're designing a new building, what I would encourage is to plan for, well, actually, so the district energy system, when you're talking about data centers, I use the word low-grade waste heat, and I said 65 degrees. I think I might have said the word ambient loop in there. So one of the next generation designs for district energy is the idea of an ambient loop, which is a modest temperature that's running through pipes in the ground that lots of buildings could connect to. And so a data center is a great source of waste heat, but you could have other buildings which could be complementary in their uses of heat. There could be an office building which has waste heat during the day, and then a residential tower next to it which has waste heat during the night, and they could be complementary buildings that could tie onto this same ambient loop. And so the idea is, if you design your building to sort of be able to take mild temperatures water, it could be like a water source heat pump system in the building or something like that. But if you're sort of accepting that kind of water temperature and you design whatever systems you have in the building for that water temperature, then it would make it quite easy to be able to interconnect to a larger district energy loop in the future. And then all you really need to be planning for is a space in the basement where you'd have a heat exchanger, and that space in the basement literally would be smaller than this hotel room I'm sitting in, or could be smaller than the hotel room I'm sitting in, because it's just not a lot of space needs. And then plan for that on the perimeter so there could be some way for pipes to get in. So it's not a lot of space requirements. The system design would be one that would be assuming you'd be having sort of this mild temperature or could exploit mild temperature water or maybe mild temperature air if it's going to be an air source system. But just it's a hydronic-based system that's able to exploit that kind of situation. And so that's pretty, you know, an engineer, I'm talking as an engineer. Engineers would really be able to gravitate towards that with just understanding that. As far as the data center, you know, we've talked a couple times, a hydronic-based system. Again, you know, think about it as, you know, there's the data center over here, there's the client over there, there's heat exchangers on both sides to hydronically separate them, and the heat exchangers, and then there's this ambient loop or this condensing water loop that goes between them or goes between them and other buildings. And so that the requirements for the buildings would be pretty simple. And just if it's a hydronic-based system, think of it as one that can capture and use low-grade waste heat that then would get boosted in the building through heat recovery chillers or heat pumps, things like that. You're done. That's all you need to do in the building. So it's either a water source heat pump building and system in the building or hydronic-based heating system in the building that can accommodate waste heat as a source. As far as then, Dale, your question was a little bit larger one, talking about how to think about the larger community. And I see we're getting a little low on time here. Can you restate that again in this context? I could try to swing at it.
Yeah, it was just the thinking long term. What can local planners or designers do in light of you know, looking 5-6 years ahead
Yeah.
to potentially cultivate the application of district energy to data centers?
Man, I mean, the proximity thing is a big one, right? You need to have, and this is the big challenge too. So I don't know if it's the answer is you want the data center proximate to where you can sell the source, right? Or sell the energy. And that means you need to have power, lots of power, and lots of people who are going to be, you know, in buildings nearby that. And so, you know, maybe there's things in the zoning that could help encourage that. Maybe there's things like that you could look at. It's actually a pretty big topic, Dale. That's actually a really big topic to talk about. I don't know if we have the time today.
No, it's for sure gonna be the topic of a future webinar, I can assure you.
Yeah.
So Dale, did you want to wrap this up?
Just wanted to say thanks for everybody for taking part. I think we got through all the questions. If we didn't, send me an email, please, and I'll be happy to do what I can to forward them to Tom and John.
Yeah.
Some of the others, but I was just, this was fantastic, Tom, John. Thank you so much.
Thank you. Appreciate the opportunity.
Great. Goodbye.